The topic of today's webinar is mammography measurements, and Patrik Andersson, our speaker today, will be your guide. Patrik Andersson is a product manager and technical expert for RaySafe X2. Welcome Patrik, and also audience today.
Hi, I will start to talk about a few different mammography measurement challenges. Then we will go through how the X2 NAM and our sensors are designed to cope with these challenges. Finally, we will have a look at some measurement examples before answering questions at the end. Let us start with some history to understand the different challenges within the field. Mammography with the intention of finding breast cancer has been a method used for over 100 years by now. But it wasn't until the 1960s that the technique started being used more systematically within healthcare. In the beginning of the mammography era, all machines looked the same. You could either use a machine with a molybdenum target and molybdenum filter for thinner, less dense breast, or you could use a machine with molybdenum target and a rhodium filter for thicker, more dense breast. In the late 90s and early 2000, the first digital mammography machine was developed, which was a significant breakthrough. This new digital imaging technique opened the door for adding other target filter combination and introducing new machine designs in the search for the best target filter combination. So, how are all the machines out there different from each other? To answer that, let's have a look at a generic mammography machine and how the different parts can vary between models. At the top, we have the anode, where the X-rays are created. The anode discs may have different angles depending on required beam quality. The anode material will of course also affect the output. The angle of the tube itself is also varying between models. The filters can be of different materials and varying thickness, and it can also be mounted flat or in an angle like the tube. The filter itself is a delicate product and highly affected by production parameters such as purity and homogeneity. All mammography machines have pedals, but those could be of varying thickness and material. All these design parameters vary from model to model, and all of them have to some extent an impact on the output of the machine. We have only been talking about the hardware to this point. All machines have highly advanced image receivers and software to increase their complexity even more. All the different materials and angles mentioned previously will affect the output of the machine. These two images show how the photon spectrum looks like for two different mammography machines. The one to the left is a tungsten anode with a rhodium filter, and the one to the right is from a molybdenum anode with a molybdenum filter. Despite similar settings, the actual machine outputs look very different. These differences are what manufacturers are trying to optimize to find the perfect combinations of things for different types of breasts. These big differences are also a challenge when performing measurements, since the dose meter must recognize the different spectra in order to calculate all parameters in the best possible way. For example, kbp. Other things to consider is the individual changes over time, namely aging of the machine, which may affect dose and HPL. With time, the anode surface will suffer from wear and tear, often resulting in reduced output intensity and minor changes to the spectrum. The filter may also change with time. This change is not related to the number of exposures like with the anode. The filter may age due to corrosion or oxidation, depending on filter material, production quality, purity, etc., etc. Manufacturers today usually have good control of their filter productions, but it can still happen. There are also other aging factors such as tube blackening and filament thinning. And I recommend having a look at our webinar, Quality Assurance Testing for Increased Patient and Staff Safety, where we talk more about tube aging in general. Other differences between machines are acquisition modes. Those refer to the different methods used to capture breast images depending on the technology and purpose of the examination. There are several different acquisition modes, but on this slide we will focus on the most common ones used during screening procedures. The most common acquisition mode during screening is still regular 2D imaging. One exposure results in a high-resolution 2D image. There is also a mode called tomosynthesis, in which the tube sweeps over the breast while several images are taken at different angles to build a 3D image of the breast. The third one is usually called combo. It's a combination of both, and depending on machine, target filter combination, anode angle, or other parameters may be changed between pulses, which means a mix of beam qualities could be used within the same screening procedure. The compact geometry of machines is also a challenge to handle. A lot of scattered radiation is created during a mammography exposure. Scatter comes from the collimator, the compression plate, from the image receiver, and so on. All this scattered radiation makes it harder to perform accurate dose and HBL measurements. And it's under these circumstances traditional ion chambers may struggle quite a bit. The tight and compact geometry makes the heel effect more prominent. There will be significant changes in dose and HBL depending on where you position your sensor. Just a centimeter or two difference will give you noticeable changes when measuring. Since there are so many parameters in place affecting the beam quality, it is crucial to have a standardized way of measuring. Otherwise, it will be impossible to compare two machines even if they are of the same model. One has therefore defined a reference points where to place the sensor during measurements. Unfortunately, this reference point differs depending on where in the world you are active. In America, the sensor should be positioned 4 centimeters from the chest wall and elevated 4.2 centimeters, while it should be positioned 6 centimeters from the chest wall and elevated 4 centimeters in the rest of the world. ACR has mentioned that one can also use recommendation from machine manufacturers for positioning. There are plenty of different machines out there, and most of them are unique in their own way, creating unique beam qualities. All machines age differently, depending on usage, material choices, production quality, etc. Different machines have different acquisition modes, and beam quality can change within the same screening procedure. Positioning is everything in mammography. The compact geometry makes it impossible to compare measurements unless you have a fixed reference point. Okay, what has RaySafe developed to help you make as accurate and easy measurements? RaySafe has developed a truly unique QA system that can handle most of the QA measurements required. The main technology in our system is based on solid state detectors, but it can also contain a pencil-shaped ion chamber used for CTDI. We will, of course, focus on the mammography piece of the system today and leave the other sensors for other webinars. It is a standalone measurement system, which means there is no need to bring a computer. It will give you all parameters needed in one view, including waveforms. The base unit stores all data while doing your measurements, and it can hold around 10,000 measurements. The system can still be used together with a computer if you would like to use the real-time export of measurement data. You can connect the base unit to your computer wirelessly or using a cable if you would like to export your data into, for example, Excel. When exported to the PC software, all waveforms can be seen in the same graph. Waveforms are often underestimated when it comes to understanding a measurement or the behavior of the X-ray machine, but they can be of great help. So let us dig a little deeper in the actual MAM sensor and some dimensions. In one of the directions, the sensor has an opening of ± 10 degrees for dose, HVL, and KVP. If we rotate the sensor 90 degrees, we have a wider opening for dose. This wider plus minus 30 degrees angle makes it possible to capture dose for the wider tomosynthesis sweep. In this case, the sensor must be placed perpendicular to the anode-cathode axis or aligned with the chest wall to capture the whole sweep. And this is how the sensor looks like if you cut it in half. The sensor consists of 4 small diodes stacked on top of each other. Having stacked diodes instead of diodes conventionally spread out horizontally enables the sensor to be much smaller and easier to work with. It also makes the sensor rotation independent, which means it will not be affected by the heel effect depending on how you rotate it. It doesn't matter if you place the sensor perpendicular to the machine anode cathode axis or not during a regular 2D screening. The sensor stack is shielded by a tin cage, protecting it from scatter radiation, which could affect measurement accuracy, giving true air chroma-free in air even in a confined space. As presented on the earlier slide, the sensor stack consists of 4 layers of diodes with different filtration. This provides 4 channels of information during each exposure. These different channels are used for optimized calculations of your desired parameters. If we start with dose and HVL, the top diode is mainly there to capture dose. But together with the other diodes, we have been able to create a sensor that can measure both dose and HVL for all mammography machines without any specific settings. This is a truly unique feature compared to other sensors on the market, which typically either only measure on certain machines or one is required to specify the anode filter combination for the sensor to get a proper dose and HVL reading. This also means that the X2 MAM sensor will give you the correct dose and HVL independent of if you have a pedal in the field or not, or if you have the sensor in front of or behind a phantom. It will even give you accurate dose and HVL readings if an incorrect anode filter combination has been selected on the X2. KBP is slightly different. As mentioned in the beginning of this presentation, different material combinations in the X-ray machine design will provide different spectrum shapes. And different spectrum shapes mean different relationship between high and low energy photons. To be able to interpret the spectrum in a proper way, one must provide more information to the system. This is why one needs to specify anode filter combination when measuring KBP in mammography applications. What is truly unique with X2 MAM compared to other sensors on the market is how we have been able to incorporate machine-specific information into the sensor. As a comparison, other sensors on the market often require input on exactly which machine they are measuring on. The X2 MAM, on the other hand, with only a few exceptions, only needs to know anode and filter combination. This has reduced the number of settings heavily to make your workflow much easier and to reduce the risk for human errors. This is just an overview to show you how easy it is to use the X2 with the MAM sensor. For dose and HVL, just place the sensor in the field, make an exposure, and read from the base unit. For KBP, add anode filter combination and make an exposure. It's that simple. A few words about contrast-enhanced mammography as well, a method usually used if the screening indicated something abnormal. Some machines have optional dual energy or contrast-enhanced mammography. These machines make 2 exposures, one with normal screening settings, and a second with higher kV, usually above 40 kV, and high filtration of copper or titanium. The second exposure is usually either tungsten copper, molybdenum copper, rhodium copper, or tungsten titanium. X2MAM will measure dose and HVL on these machines perfectly fine. KVP, on the other hand, is a bit more challenging. We therefore recommend using our RF sensor when measuring KVP on these machines. The good thing about using the RF sensor is that no settings whatsoever is needed. Just place it in the field, make an exposure, and read KVP from the base unit. And to demonstrate how easy it is to use our X2MAM sensor, we will show you a short 2-minute video.
Today we will demonstrate how easy it is to measure with the RaySafe X2MAM sensor. In this demo you will see how you can get dose and HVL without knowing the machine specifications such as target filter combinations. We will also show you how to get a valid KVP without knowing the filter thickness. Turn on the base unit. Then connect the sensor. Place the sensor on the examination board according to applicable regulations. In Europe, that is 6 centimeters from the chest wall and elevated 4 centimeters. In the US, it's 4 centimeters from the chest wall and elevated 4.5 centimeters. Make an exposure and read the values. Here you can see HVL, and if you press dose rate and swipe to the left, you will also see the waveform of the dose rate. To get a KVP, you need to specify the target filter combination of your machine. Swipe to the left and choose the correct setting for your machine. In this case, we're using a Pristina Molly Molly with a pedal. Press the home button and make another exposure. Now you've also received a KVP. If you press the KVP and swipe to the left, you will also see the waveform of the KV.
A summary of the sensor design. As you understand by now, there are plenty of different machines on the market, and they all differ from each other. But the X2MAM sensor is designed to help you handle all variations. It can measure dose and HVL on all machines without any settings at all. Just place the sensor in the field and start measuring. KVP requires a setting, but our selection of settings is typically much smaller compared to mammography sensors of other brands, simply because of our robust and well thought through sensor design. To increase automation, you can easily connect the MAM sensor to a computer for data export with cable or wirelessly. On the raysafe.com website, you find the list of all validated machines for RaySafe MAM sensors. It is named Mammography Coverage Table. If you have additional questions regarding measurements, you are more than welcome to contact our technical support. A useful setting in the X2 system to know about is stop delay. It is a very handy tool if you are dealing with several exposures in the same screening. The setting is easily accessible from the settings in the base unit. What it does is that after an exposure, the system will wait a certain amount of time before the measurement ends. The system is still active during the stop delay, waiting for more radiation to be included in the same measurement. And why is this useful? In this example, we are looking at a measurement from a Siemens Mammomat installation. First, it will do an AEC pre-pulse. Then it will use the pre-pulse signal to calculate the correct settings for the exposure. It will do the main 2D exposure. It will change the grid and make the last exposure. With a long stop delay setting, everything is captured in a single measurement, and you can easily get an overview of what the machine is doing. If you use a short stop delay, the screening will be divided into 3 separate measurements. It's harder to understand the behavior of the machine, but it makes it easier to investigate certain part of the screening. The RaySafe X2 is faster than other instruments, and it's able to capture a new measurement immediately after the previous. Another example is this tomosynthesis machine from Hologic. First, it will do an AEC pre-pulse and use the signal to calculate the correct settings for the tomosynthesis. Then it will perform the short pulses at different angles. It will switch filter, another AEC pre-pulse, and finish off with a 2D exposure. A long stop delay gives a good overview of what the machine is doing, and a short stop delay makes it possible to easily investigate a single pulse in the tomosynthesis sweep. To conclude this presentation, I would also like to say a few words about some of our complementary sensors. You need to do more measurements than just in-beam measurements on mammography machines. The first is our X2 light sensor. It is a state-of-the-art light meter used for calibration of medical monitors to make sure any image looks the same on all medical monitors. It is not only a luminance meter, but also an illuminance meter for light intensity measurements. It can talk directly to the Varco and the ESO calibration software if needed. The second is our X2 survey sensor, a sensor designed to measure scatter radiation or tube leakage within the diagnostic range. It has auto trig mode or manual mode for extremely low intensities. The third is our pocket size DXR Plus. It is used for adjusting the X-ray and light field alignment, which is also needed for most QA tests within mammography. And finally, a few words about phantoms needed for the image quality tests. The small-sized RaySafe ProMam biopsy phantom permits fast and easy quality evaluation of conventional and digital images. Image quality can be evaluated with a single exposure, and the test objects are similar to those specified in the 1999 ACR Stereotactic Breast Biopsy Quality Control Manual specified by the ACR. A very short summary. Measuring on mammography is challenging. The small, compact geometry in combination with various machine designs makes it hard to accurately describe or estimate the output. Your best ally in this is our RaySafe X2, which will provide you with state-of-the-art technology and superior ease of use. Measuring on mammography has never been easier. RaySafe X2 will guide you in the best possible way so you can excel in your role. Thank you.
This concludes today's webinar session, and I would like to thank you, Patrick, for a fantastic presentation, and a huge thank you also to our audience today for your time and attention. Attached to this webinar and on our website, raysafe.com, you will find even more information. Now it's time for the questions and answers section, and you are encouraged to stay with us and share your questions. If your question will not be answered today, we will get back to you via email. Now let's see what we have for you to answer, Patrick. First question is, how should you place the sensor when measuring on tomo machines?
Well, if you measure during tomosynthesis, you need to place the sensor perpendicular to the anode-cathode axis, since the X2 has a wider opening for dose in that direction and can therefore capture the whole sweep. So for tomosynthesis, it's perpendicular to the anode-cathode axis.
Can you comment on RaySafe X2 accuracy versus RTI?
We usually do not really comment much on our competitors. What we can say is that we are very proud of our own accuracy and especially stability and repeatability, where we historically at least have been superior on the market, and I believe we still are.
There is no KV mode for rhodium, so how can KV be measured for this combination?
When we measure KVP, it is the potential over the tube itself, and the potential is the same no matter if the target filter combination chosen. And rhodium machines usually have molyrhodium as well, a combination where we can measure with the X2MAM. So it's perfectly fine to measure KVP on molyrhodium instead of rhodium.
Okay, so does a paddle within the X-ray beam affect HVL measurements?
Yes, the short answer is yes, it does. So pedals can differ depending on manufacturers and so on, but you can usually translate a pedal to an additional 1 to 2 millimeters of added aluminum equivalent. And added aluminum or added filtration will of course affect both dose and the HVL.
Did you say that the X2MAM sensor measures independently of the 4 and 6 centimeter sensor positioning from the chest wall side?
No, not independently, no. So you have the heel effect and the anode cathode direction, meaning that you will get different dose and HVL if you move the sensor in that directions, in the anode cathode directions. And this can give minor changes to KVP and dose and HVL, and it will definitely get you different readings on dose and HVL and minor on KVP. But this is the reason why it is important to have this reference point, which I was talking about in the presentations, to be able to standardize your test so you are able to compare your results within or between different machine types. So dose and HVL are really not sensitive if you're measuring or if you move it in the different direction, perpendicular to the anode cathode axis, where we don't have any heel effect. But in the heel effect direction, both dose and HVL will change, and also minor changes to the KVP.
Okay, why is there a special setting for a Pristina machine?
Well, Pristina machines has slightly different photon spectrum compared to other moly machines because of their internal design. So we need to have a separate setting for this machine just to handle their specific design and their specific shape of the spectrum.
If I have a 5-second exposure and my stop delay setting is at 4 seconds, does the sensor stop measuring at the stop delay, or will it measure for longer than the single exposure time?
No, the stop delay is the time between exposures or pulses. So the stop delay clock will start ticking as soon as the exposure or the pulse has stopped. So if you only have one long exposure, then it doesn't matter if you have a short or a long stop delay. And I would suggest having a short stop delay because that will speed up the process a little bit.
Okay, so anyone else? Yeah, here we go. When the sensor is sent for calibration, do you automatically calibrate the sensor in all target filter combinations available for your unit, or only at the user's requested target filter combinations?
Well, we have quite a lot of different combinations during calibration, actually. We don't have all combinations, but we have almost all of them. So it's a standard calibration, so it's not upon request from customers or anything like that. So it's our standard calibration, which is at this stage also ISO 70025 accredited. And this is a quite big, I would say, advantage to compare to our competitors, where they usually calibrate in just one beam quality and then they use correction factors to compensate for this, while we, on the other hand, have plenty of different combinations in the calibration itself.
Okay. Anyone else have something for us today? I'll give it a couple of seconds more and see if we get something, or if this actually was the last question.
Yeah, we'll see. Please go ahead, submit your questions if you have any. Still no questions? Well, in that case, I would say that this concludes today's webinar. And thank you so much for the questions you have submitted today. And I will hand it over to Lena just to say a few final words.